What we want to do is the following. We want to determine the configuration bits for the circuit shown in the figure to be implemented on our 2x2 FPGA device. Within this context, we are assuming that the circuit we have to implement has been properly described by using an HDL specification. But just to make it more clear, within online video, we are working with its graphical representation. Said that, this means that we can consider our graphical representation of the circuit as the results of the synthesis phase, and that we are ready to pass it to the following one, the technology mapping phase. As we know, the technology mapping phase is the phase in charge of finding the best technology implementation for each of our elements by using a technology library. In our example, a first solution can be the one shown in the figure. We have 3 logic components and we are going to map each of them onto a CLB. This is definitely a solution, but maybe we can argue that this is not the best one. We may also want to spend a bit in elaborating what we can consider as the best, but so far we can consider this as the number of resources we are using to implement our specification. This is not the only way of doing it, but we need something easy and clear to be understood to drive our process. Therefore, it can be a reasonable metric. Now, let us see if we cannot do any better. This second solution is providing us a better outcome for our technology mapping phase. With the previous solution, we were using 3 CLBs, while now we are just using 2. Which means 33% improvement in terms of resources. Not bad at all. Now that we know that we are going to have 2 CLBs, CLB-X and CLB-Y to implement our system, we are interested in knowing which ones of our 4 CLB are going to be used. In the figure, we can see that all of the 4 CLBs are good candidates for being configured to be CLB-X or CLB-Y. How to choose? Well, that is exactly, as we know, what the placement and routing phase is here for. Let's go first with the placement. At the very first sight, just to guide you through the entire process, let's try to place CLB-X onto CLB0. That means that we are going to configure the top left corner CLB with the logic of CLB-X. Now, done this, we can move to find a placement for CLB-Y. Again, we have 3 CLBs that are all good candidates. Let's just pick one. And by doing this, we are configuring CLB2. That was the one on the top right corner with the logic of CLB-Y. Now, I was really keeping it simple, but still, this is the placement and routing phase. Therefore, we may have found a placement, but what about the routing? The routing phase is used to connect elements together. That means that we have to properly connect the placed CLBs, but also that we need to interconnect them with the proper I/O blocks. Otherwise, data won't be able to flow in and out our system. Just consider the connection with the input blocks. CLB-X is waiting data from inputs 0 and 2, while CLB-Y is looking for data coming from the output of CLB-X and input 1. This was something that we were aware of because of the netlist we had, and it can bring to a routing using 3 switch boxes as shown in the figure. Now, the question is, as we did after the first solution during the technology mapping phase, can we do any better? Well, in trying of doing it, we have to go back to our placement phase and we have to try a different solution. We previously mapped CLB-X and CLB-Y onto respectively CLB0 and CLB2. Now, what if we are going to change the placement of CLB-Y? What if we are going to place it on CLB1? Well, from a pure placement perspective, that doesn't seem to introduce any improvement, but it doesn't add any worsening either. Therefore, it can be an interesting solution to be explored. Just a second. Before continuing, I do have to add a note here. In fact, I don't want to give you the impression that worsening solution does not have to be explored for granted. It does all depend on the algorithm we are using to drive our placement phase. A simulated annealing solution will definitely try to explore also some of these situations. Now, let's go back to our new solution where CLB-Y was mapped onto CLB1. By using this new placement solution, we can run our routing algorithm again, and there we go. We do have a much way better solution with respect to the previous one. Before, we were using 3 switch boxes, while right now we found a solution that is using just 1. Well, that's huge. We got a 66% improvement by just moving CLB-Y. That's great. We are training up. But we are not done yet. We need to connect our elements also to the output pin. Data has to be provided to the external world. Again, as you can see, this process is definitely complex. I'm facing it as a sequence of independent subproblems just to let you get the feeling of the underlying complexity. But in reality, things are much more complex, and this is why we are saying that we need automatic tools to assist us on this. Starting from our best solution, we can now try to complete our design by connecting CLB-Y, which means CLB1, with the output block 07. This figure is presenting the solution we have been able to obtain. As we can see, we are using two CLBs to implement our specification, and two switch boxes to drive our signals. Can we stop here? Oh, come on! This time the answer was easy. Obviously, we are not going to stop here. We do have to try a different solution. Again, deciding whether to stop or not is not something that is going on us, but it's something that we have to pass to our algorithms. Therefore, it's necessary to find a stopping criteria to see if it can be worthy to try to find a better solution or not, once that we have been able to find one. To try a different solution, we have to go back once more to our placement phase. We were playing with the CLB-Y placement, and we are going to do the same now. We try to place it on CLB1 and 2, let's see what is happening by placing it on CLB3. By doing this, we have a solution which seems to be very close to the previous one. We're starting from a solution based on two CLBs and two switch boxes, and we end now with a solution that is using, again, two CLBs and two switch boxes. Well, that's true. But are these two solutions really the same? To properly answer this question, we may want to add the internal configuration of a switch box into the decision process. We know that each switch box is driving 3 lines. Therefore, instead of only considering the number of switch boxes used to implement a solution, we may be interested in knowing the number of lines used to implement a solution. With this observation in mind, let's go back to our two solutions and see if they are really the same. The last solution we have been able to find was configuring CLB-X onto CLB0 and CLB-Y onto CLB3, and it was using two switch boxes, SBO and SB3. By doing this, we are configuring one line in SBO and one line in SB3 to bring the CLB-X output to one of the inputs of the CLB-Y. Furthermore, to connect input 1 to the second output of CLB-Y, we are using a second line in SB3. Within this context, the overall number of lines used to implement the proposed solution is 3. Let's see what we can obtain from the first implementation we found. The solution was configuring CLB-X onto CLB0, but CLB-Y was mapped onto CLB1. From a switch box's point of view, we were using the same set of the one used in the previous solution, SBO and SB3. But we can appreciate the decision we made in having a different placement for SBY. In fact, by having it mapped onto CLB1, this implies that we are still using one line to connect one input of CLB-Y with the output generated by CLB-X. But we are going to need only one line in SB3 because we just have to connect the output computed by CLB-Y to the output block 7. And this will help us in deciding whether to go with this or with the previous solution. And I guess we know which one we are going to choose, right?